Hello and welcome to this lesson about parts of quadratic functions. The goal of today is to be able to identify parts of a quadratic function. And we'll be doing this in two ways. We're going to take a look at the equation and we're going to take a look at the picture, the graph itself. And so just to kind of give you a brief summary of what it is we're going to do, keep in mind the generic form of a quadratic function, which is ax squared plus bx plus c. There's valuable information in this equation that we're going to learn to extract, so we know what the graph looks like. We know something about its direction. We know something about where it crosses some places. A lot of that can be learned just by looking at the equation. At the same time, we're going to take a look at the graph. And now, all quadratic functions take the form of a parabola. And what changes is where the parabola is. So we could have a parabola that looks like that. We have a parabola that could be way over here. We have a parabola that could be like this. But a parabola is sort of this U-shaped graph that comes from a quadratic function. And there are certain pieces and things that we can extract, or pieces of information we can extract by taking a look at the graph. So let's take a look at some examples of a graph. Or first, before we do that, let's talk about terminology. There are a couple of terms that we need to be familiar with. The first one is vertex. The vertex is either the lowest or the highest point on a graph, high point, of the parabola. That is where the U part takes place. Then we have the axis of symmetry. The axis of symmetry is a vertical line, so it's going to be x equals some number where all the points are mirrored of a parabola from the left-hand side to the right-hand side. It's one of those things that's hard to describe right now, but once you see it, it'll be quite easy to pick up on. Next, we have the direction. The direction refers to, is the parabola looking like that, or does it look like this? And what's really cool is that the direction of a parabola is determined by one thing, and that's a, in ax squared bx plus c. So ax squared, all that stuff. If a is greater than 0, it goes up. If a is less than 0, meaning it is a negative number, it points down. And also what that means is that then the vertex, so the vertex is that point there and that point there. If a is greater than 0, we're going to have an absolute minimum, the lowest point of the quadratic function. And if a is negative, we will have a maximum, the largest value that the quadratic function acquires. After that, we got a couple other things that we've seen with linear equations. And so one of them is the x-intercept. So the x-intercept is where the function crosses the x-axis, but the other thing we have to keep in mind, there are two things actually. One is that it's actually, those are the solutions, or solution, depending if there's only one, to the quadratic equation. And then the other thing we also have to keep in mind is that they may not exist. There are some quadratic functions where no matter what value you plug in for x, you cannot get it to equal 0. The final one we have is the y-intercept, and this one's easy. So the y-intercept, going back to our equation, ax squared plus bx plus c, is simply c. All right. So that is when the graph crosses the y-axis. So enough talk about all these terms. Let's look at some pictures and see what we can do with all this. Okay, so let's take a look at this graph right here. We got a quadratic function. We don't know the actual function. All we have is the picture. But from this picture, we can pull certain details. So for example, we can pull the x-intercepts. The x-intercepts are going to be points. So the left one is going to be 0, 0. That's right there. The right one is going to be 6, 0, which is right there. And so that means 0 and 6 are both solutions to this quadratic function. The y-intercept is also 0, 0 because it's going through the origin right there. Taking a look at the next piece of information we might want to find out, and this is crucial, the vertex. When does it start to turn around and go back the other way? And that vertex happens to be a 3, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. Vertex is at 3, 9. Taking a look at the picture, it is a maximum value. Something else we can take from this is that a is a negative number, a is less than 0. And finally, the axis of symmetry. The axis of symmetry is just always going to be that x value of the vertex. X equals 3. And what the axis of symmetry does is anytime we find a point, so like right here or right here, notice how it's 2 away from that axis. It's symmetrical. Down here with our intercepts, 3 away. So if you have a point on one side of the axis of symmetry, you can automatically plot it on the other side. Let's take a look at another example. So here's a new graph, but we're going to be looking for the same things. X-intercepts, Y-intercepts, the vertex, the axis of symmetry, whether it has a min or a max, all that stuff. So taking a look at the x-intercepts, I see those right here and right there. And so that is 2, 0 and 3, or 4, 0, I should say. 4, 0. Next, let's look at the y-intercept. All right, this one's a little bit tricky, but it's right there. So that's at 0, 8. Now we'll work our way to the vertex. The vertex down here at 3, -1. And given that the parabola is forming a U going up, that means it is a minimum value, not a maximum value. And then the axis of symmetry is just always that x value. X equals 3. So not doing the best line drawing a dashed line there, but what that again means is that if you go 3 spots this way and you found a point, you can go 3 spots that way and match that point. Now let's switch it up and let's go with an equation and see how we can extract similar information from an equation. So let's consider the quadratic function x squared minus 8x plus 7. Now with an equation, we can find a lot of the same information we found on, or with a graph on this side right here, but it requires a lot of work. So today we're going to focus on these 3 parts: x-intercepts, y-intercept, and direction. Now the x-intercept, keep in mind how we defined it. That's the solution to the equation. And so that's when we're letting this equal 0 and we solve it. So we have to factor and then work back and solve each factor for 0, and those are x-intercepts. So for example, here is x minus 7, x minus 1, and so our intercepts, keep in mind the sign's going to change from here, are going to be 7, 0, and 1, 0. The intercept, that's an easy one. That's just that number right there. So that's going to be 0, 7. Done. And also, the direction is easy. For the direction, we look here. There is a phantom 1 next to our x squared. That 1 is positive, and so our direction is up, meaning that it's going to look like this and not like that. So I'll give you another example, but that's how we extract some of this information from the equation. Now, let's consider this equation. Negative x squared plus 4x, and that's it. Our x-intercepts, we need to factor it. So what I'm going to do is take out a negative x. So I take out a negative x, that leaves me with 1x, positive x on the inside, minus 4. Now the reason why I did that, because the solution here is just going to be 0. So that's 0, 0. Here, now it's a little easier to look at and just to realize that the other one's going to be 4, 0. If I had not taken out the negative and I just went like, x and then made it negative x plus 4, I'd still get there, but it makes it a little more complicated, and we leave negatives floating. Again, it's tricky. The y-intercept, there's no c. There's a blank here where c ought to be. And so that also means that it's just going to be 0 and it's going through the origin. So this is one where the x and y-intercepts are at the same point. And finally, the direction. I look at this point right here. I see it's negative, so that means that it is going down. So it's going to look like that. So final thing I have for you is how to use some of this information to complete a parabola. So here we have an example of a graph that has not been completed. And we're going to try to find the points that are reflective to those 3 that I just drew. Let's call them A, B, and C. Now, what we're going to notice here is that down here we see where it starts to curve back up, meaning that this point here is our vertex. And that means that we have a line of symmetry that goes right through there. And so notice how from here to here is just 1 point. So I can go right 1 point on the x-axis, and I'll find the reflection of C. So let me just make a quick table. We have, oops. So on this side are the original, or on this side are the original points, and then these are going to be the new points. So let's see here for C, it's going to be at 1, 2, 3, 1. So 3, 1. For B, I moved over 2 spots, so I move over 2 spots here, and that one's going to be at 4, 4. 4, 4, make that a little neater. And then for A, I'm at 3 spots. I got to go 1, 2, 3, 4, 5, 9. And there, I've found these points, and if I wanted to, I could draw the graph going through those points. The key here is to realize that there's an axis of symmetry at the vertex right there, and then to measure how far the original points are from that axis, and then I can use that to go the other way. So, in a nutshell, that's an introduction to the pieces of quadratics. Let me know if you have any questions.